Okay, can you hear? All right. So yeah, this is joint work with my student Yuantian Ding. Unfortunately, he could not be here due to some visa issues, so I'm here to present. So the talk is about syntax-guided synthesis, or SyGuS. The idea is that to capture the user's intent for a synthesizer, we need to provide not only semantic specifications, which talks about what the program's supposed to do, what's the functionality, but also syntactic constraints, what the program should look like, right? That can dramatically reduce the search space and help the synthesizer find a solution faster. So let's take a concrete example to see. Hacker's Delight example number 25 in SyGuS interchange format. The SyGuS interchange format is a common format to represent SyGuS problems and accepted in many competing SyGuS solvers. And Hacker's Delight is just an excellent book which exhibits a lot of interesting examples of tasks that can be represented using bit vector expressions. So a lot of tricky and elegant examples, but from the point of view of synthesis, they are extremely challenging. Okay, in the example 25, it just says, compute the higher order half of the product of bit vectors x and y. Okay, this task can be translated into a bunch of examples from the point of view of programming by example, right? So we have some random examples. For example, if x equals 8000, y equals 0088, then the output should be 0055. And you can have a bunch of examples to characterize the specification. And besides this semantic specification, we also ask for a syntactic constraint, basically what operators you are allowed to use, right? This could be quite arbitrary, but you want to allow most common bit vector operations and get it represented as a context-free grammar. And here, the interesting thing is that you can you can provide some constant as your hint to the synthesizer, right? For example, the 00FF is just a mask of the second half of the bit vector, right? So because the question explicitly asked about first half, second half, this could be a key constant that help you distinguish first half and second half. And the number constant 8 is just number of bits you want to shift if you want to switch between first and second half. All right, so we don't really know what the program is, but we know, okay, these are probably what you want to use. And taking both the two pieces, the syntax-guided synthesizer is supposed to generate a solution which satisfies semantic specification, also follow the syntactic constraints, which is an instance of the grammar. Okay, for example, this on the screen, this is a solution found by our SyGuS solver DryadSynth. So it looks not so difficult, but it's already beyond the capability of all existing SyGuS solvers. And this talk, the contribution of the paper is mostly about the techniques behind how we find solutions for challenging problems like this. Okay, before I tell you what we did, let's see what has been done in the community. Okay, for bit vector synthesis, or more generally, syntax-guided synthesis, there are two major approaches. One is bottom-up enumeration. So you have a syntax constraint that represents essentially a search space. You have an infinite space of candidates from the search space, and the synthesizer is just going to take a semantic specification and search for a solution. And because the search space is infinitely large, the key question is, how do you search, in what order? Right? The most naive way is to search based on size. You start from the smallest possible solutions and move on to larger ones. And also you can do better search if you get equipped with equivalence, right? Some candidates could be semantically different, but essentially the same programs. They are semantically equivalent, so you don't have to search all of them. You can search one of them and discard a lot of solutions. So the next talking session is about observational equivalence. So, but in different contexts, but you would get the idea as well. And of course, you can do probability-based search, right? You can, not all candidates are born equal. Different operators have different likelihood. You can assign some probability, and you can steer the search better to a solution. Okay, you have a lot of interesting ideas going on. And another big idea is top-down deduction. you take the semantic specification and ask the question, what can be the top level operator? Okay, if you pick one operator, for example, you want to have an add, then the question is what can be the left operand, what can be the right operand? And you can split the specification to two sub-specifications, right? And the two subtasks can be divide and conquer, and you can keep doing the splitting downward. Okay, this is another major idea, and you can imagine that there's a lot of novel ideas to combine these two ideas, right? So, for example, you can do top-down deduction to get the top-level operator synthesized, and from the leaves, you can also start from small enumerations, and the two directions meet in the middle, something like that. A lot of interesting ideas, but the question is, do they really work for bit vectors? Well, not really, because evidenced by a lot of unsolved problems like Hacker's Delight. So what's the problem, right? So what makes bit vectors so difficult? So from the point of view of top-down deduction, the problem is that you have too many different ways to decompose, right? Even if you have a very simple example, you have two inputs, 1, 1, and 1, 0, you want to have 0, 1 as the output, right? So what can be the top-level operator? It turns out to be the case that almost every operator can serve as a top-level operator. And even if you stick with a single operator XOR, right, it's not too hard to figure out that you can have arbitrary combination, right? So the left or right operand can be 0, 1, 1, 0, 1, 1, 0, 0, right? And if you have, well, 64 bits or something, it can be a disaster, as you can imagine. So it does not really helpful if you have so many different ways to decompose. And bottom-up enumeration, of course, we know that there's an exponential blow-up, but things are especially bad when it comes to bit vectors because you have more than a dozen commonly used operators, right? The search space grows extremely fast when you have larger expressions. So our first idea is to have a normal way to combine the two directions, which we call bottom-up deduction. So what does that mean? Let's take a look at a different example. So Hacker's Delight, example number 19, difficulty level 5. I put the example here, but you don't really have to understand it, right? All you need to know is that you want to synthesize a function with 3 parameters, x, m, k, and the arrowed bar shows the order of search if we follow the size order strictly. And if you search along the way, at some point, you can find the expected solution, right? But you have to search an astronomical number of candidates before you can hit the candidate. And you can do a lot of probability equivalence techniques, right? You may get 1 or 2 orders of magnitude speed up, but that does not change the story much. So what do? We can keep multiple pools of candidates. Okay, what can serve as, if we want to have XOR as the top-level operator, what can be the left operand or what can be the right operand? And when we get to a candidate, Kasai left shift K, okay? This is not a solution, obviously. But note that this is actually the right operand of the expected solution, right? We can reason, we can do a deduction and determine that, okay, it can serve as the right operand of a solution. If the top-level operator is XOR, we don't really know what the left operand could be. We don't know if that part will cooperate. It's just angelic wishful thinking, and we just keep the candidates there in the candidate pool. And later at a point, we find the other piece of the solution, and we can put it in the left operand pool. Right? XOR is commutative, so we don't really have 2 different pools, but conceptually we have 2 different pools. But once we have the 2 pieces, we can immediately put them together and check if they can be combined to find to be a solution. Right? That makes the search much faster than a brute force search. So that's a bottom-up deduction idea. it can help us solve the Hacker's Delight number 19. But for 25, we still need a final push. We need another pair of techniques. The second one is term graph-based enumeration. So look at the solution. We have the Xi, which is a commonly used subexpression. In the tree representation, it makes the tree really large. So this is quite common. You see many common subexpressions because for bit vectors, you don't really have functions, right? So if you have some common components, you have to repeat. But if we do a term graph representation, you just have one single copy of the common shared subexpressions. That makes the representation much more compact. And if you search along the side of the term graph, you can prioritize the search to these kind of expressions. All right, this is a very simple idea, but we were a bit surprised that it's not actually explored in the community. And it helped a lot in some cases. So one more thing is large language model guidance. Well, in 2023, when we prepared for the submission, it's not too surprising that we ask ourselves, oh, can we get the job done by ChatGPT? Right? We did try. The good news, or I should say bad news, is that ChatGPT cannot get it solved. Right? But if we lower our expectation, if we say, okay, can you give us some useful sub-expressions that we can reuse? And it did quite a good job. And if you ask a question many times and you just see what's the repeatedly proposed sub-expressions, it becomes quite robust. You get some key components suggested by ChatGPT. Okay, for example, here, the P1, P2, P3, P4, right? You have the upper half of X product with upper half of Y, right? The combination of upper half, lower half of X and Y, right? That's quite understandable because in the prompt we have some keywords like product and higher order half and lower order half, right? They kind of capture the keywords and knows that the product of these combinations, higher order half, lower order half, can be helpful, right? So they are actually helpful. This, if we give these components as hint to a synthesizer, right? So this could be used for extended grammar. So we can get the search much more efficient. All right, so let me move on to evaluation. So we have implemented all the ideas in our SyGuS solver called DryadSynth. It was a SyGuS solver just supporting conditional linear integer arithmetic. Now it supports bit vectors as well. So if you, and it's available if you have any synthesis questions, give it a try. So we have tested over 20 benchmarks from Hacker's Delight and more than 700 benchmarks from the SyGuS competition and 500 benchmarks on deobfuscation. And we compare the performance with CVC4, Droid, Probe, and Simba. Okay, all state-of-the-art SyGuS solvers. So how many can be solved and unsolved? It turns out that we can solve all the problems from Hacker's Delight and case splitting. We have 15 problems unsolved for deobfuscation. This is better in every category than every other solver. And some benchmarks were solved by only one solver. DryadSynth uniquely solved 31 benchmarks. Simba solved 4. Droid solved 3. Here's the result for Hacker's Delight. So starting from example 19, going on, they were not solved before, right? And for the simpler ones, we are like one order of magnitude than existing solvers faster. Here's a cactus plot for performance on case splitting. We are consistently faster than other solvers. And in terms of size, the solution size, we were not smallest one for easier benchmarks, but it tends to be smaller when benchmarks are more challenging. And we have similar observation for the obfuscation benchmarks. So I'm running out of time, so I don't want to talk too much about ablation studies, but takeaway is that every single idea is critical for some of the benchmarks, and we have all these techniques combined together, we can get all the Hacker's Delight benchmarks solved. All right. So yeah, that's what we have, a bunch of techniques: bottom-up deduction, term graph-based enumeration, and large language model guidance for bit vector synthesis. But I think the techniques can be general and useful in other contexts as well. So thank you for your attention.
Questions?
Nice talk. Just a question. So this, you evaluated on bit vectors, but it seems like the techniques could be useful in other settings. Have you evaluated DryadSynth on other SyGuS benchmarks?
We had the CLIA solver. The DryadSynth was built for CLIA. We had a PLDI-20 paper talking about our algorithm. But when we move on to bit vector, we found it's extremely challenging, and we need a set of new techniques to address bit vectors. But yeah, I think the techniques can be generalized. We are revisiting CLIA algorithm and see if they can be helpful in that context as well.
Hi, great talk. I had a question about the bottom-up deduction step, specifically when you have something like something left shift by k, is that a complete term, or is that a term with a hole in it?
This part?
Yes.
So can you repeat your question?
Yes. So basically, when you're saying that I can put something like something left shift by k on the left side or on the right side, is this a complete program term? Like, is this something that you know what it evaluates to, or is it something where you don't know what you're left shifting yet, I guess?
So when you put a candidate in the pool, it means that it's a potential candidate. Okay, it can serve as left or right operand of an XOR. I don't know what the other operand could be, but it's satisfiable, right? It's if I can find a solution on the other side, they put together can form a solution. I don't have a full solution. I have a partial solution. I just keep the candidate in the pool and keep moving on the search. So I'm keeping multiple pools, right? So for XOR, I have left pool, right pool, right? So what's the left operand, what's the right operand? For each operator, I'm going to keep a bunch of candidate pools, right?
Okay.
And it's not necessarily just one level. Sometimes we do two levels. XOR, what's the left operand, what's the right operand. So if we keep enough number of pools, that we can eagerly find candidates so that they can put together to form a full solution.
Okay, yeah, so I understand the part with the pools. I think the part that I was confused by is like maybe a concrete example would be, would this term look something like x plus 3 left shift by k, or would it be something like I don't know plus 3 left shift by k? Like basically, is this a term that you can evaluate already when you put it in the pool?
Yeah.
It is.
If
Okay,
you put
great.
something, it's already.
Okay, thanks. That's just that was my question.
Okay.
If there is no more questions, let's thank the speaker again.